There we go. That's it. All right. Okay. Marco is Senior Associate Mechanical Engineer with PAE, a firm widely recognized for thought leadership in sustainable design. Marco has over 10 years of experience in systems design and project management. He is skilled at designing energy and water-efficient systems that meet a wide range of budgets. Please welcome Marco.
Forward and backwards.
Great. Thank you. So, this presentation is going to cover a lot of material. We have about 50 minutes is what we have scheduled. I have a lot of slides, ground to cover. I'm going to go a little bit fast, so not too fast, but just ask questions as we're going through it. And this presentation is focused on zero energy as well as water design and how geothermal is being used to achieve that at this point. So,
Go ahead.
All right. So here's the agenda. We're going to talk about a holistic approach towards zero energy and water design, how we typically do it. It's just sort of a formulaic approach that we have, tends to work very well. How geothermal, we see it as a solution towards California zero energy and water. There's not quite water goals yet, but hopefully there will be soon. And then we're going to talk about 4 case studies that exemplify the design and the goals that we're trying to achieve. So about just PAE really quickly, we're sustainably minded, innovative firm, and this is sort of our portfolio. The latest thing that we've been focusing on is on living building design, so we're pretty excited about one of the projects we're going to be showcasing. So let's dive right in. In terms of how we approach sustainable design on the energy and water side, we have this broad formulaic approach that works pretty well for us. We set aggressive goals, obviously, having the client on board from the get-go and always shooting for a little bit higher than what you really want tends to work really well. Look at the data and site resources, then work on reducing energy. And then after that, we look at systems, then we make up the energy that we need to make up, and verifying performance and learning from the projects that we design. So setting aggressive goals, there's a lot of different sustainable guidelines these days, Living Building Challenge being one of the latest ones that we're designing towards. Some of our projects, Passive House and MinerGP, have been showing up quite a bit as well as in our portfolio, and they're great sustainable guidelines as well. So what do we mean when we talk about analyzing site resources and climate? This is San Francisco data, and if we take the approach of designing a building towards code, we would have all the hours on the left, 3,300 hours of heating, and about 133 of cooling we would need to provide. So we'd need, first of all, we would need a heating and a cooling system. Second of all, we would need to expend that energy. If we do our homework and design a good envelope, there's no reason why we need a heating system in this climate. We've done this in the Pacific Northwest, where the design temperature is a -2, and it's worked pretty well. And so, I mean, there's no reason in our climate why we wouldn't be able to do this. So we have a few hours, maybe 54 hours. In San Francisco, obviously, some other climates in California, this wouldn't work as well. You could do it on the heating, on the cooling. You might need to look at some other strategies like phase change, et cetera, to get you to the least amount of hours that you can in providing cooling. But the point being that we're really trying to avoid heating and cooling if we can and use passive systems. And the envelope design is a big part of that. So this is just a synopsis of the typical amount of energy that goes into the different components in the envelope, infiltration being one of the big ones, especially in that cold-dominated climate. And why is this important? Well, we sort of have this slide of way back when with mud huts. Maybe we had an R3 overall, then moved on to log cabins, improved a little bit, and stake frame homes, R16, and now we're sort of back to an R3. So it's very important to do your homework in terms of envelope design. We're mechanical, electrical engineers, but a lot of the analysis that we do is related to envelope design, a lot more in the front end of projects. So then other things about site resources, it's not just the climate, the rain, et cetera. This is a Loney College, and one of the things that we'll talk a little bit more about this project, but in this case specifically, this project was so close to the bay and the water level was so high that geothermal made all the sense. And one of the other items that came into play here is that this site was contaminated from agricultural use, and so it had to be cleaned up, and so it had to be excavated some. And so when you do that, you're going to spend the money in any case. So throwing slinky coils, it's almost a no-brainer that you're going to get the benefit of geothermal performance. So looking at all resources that you have from your site, and then after you're done looking at your resources, envelope design, et cetera, looking at reducing energy use, and one of the gentlemen here pointed out, what about users? So that's a big part of zero energy design these days, is you can design the best building, but if the users are not on board, it's going to be really hard to get there. And one of the key components of making users be on board is giving them data, letting them know how much energy you're using. So whether it's mobile devices, whether it's something on their desktop, that's a key component of getting to zero energy and water design. Then we're looking at MEP systems. We do tend to look at passive and tend to exhaust these as much as we can. Daylighting, thermal options, phase change, good envelope design. And if we, at that point, if we need heating and cooling, then we move on to active systems, geothermal being one of them. So there's a lot of options out there. We tend to focus on a few, maybe 10 or 15, and then dive deep into about 5, depending on the project, and do some energy analysis to really get to the bottom of what the best fit is going to be. So geothermal is right there, part of an active system. And once we're done with our MEP system analysis, we look at renewables, how we're going to make up the energy and water. So solar income, rain income, wind, and geothermal. Obviously, we're not talking about this type of geothermal here today, but you get the point. Last thing is verifying performance and learning from our projects. So this is the Bullitt Center up in Seattle, and at this point, we have about 2 years worth of data for this building. It's 90% occupied, and the graph down at the bottom left is the energy use for 12 months worth of data. And 2 weeks ago, actually, this building just became officially the largest living building in the world. So 50,000 square feet is not that large, but when you compare it to all the other living buildings that have been certified to date, it's a big thing. We'll talk more about this in a little bit as well. So now we're gonna look at for California specifically, and you can take this more broadly in terms of goals and status, and how we're going to achieve zero energy, zero water design. And the graph here also suggests, food resources and other sustainable items, but we'll focus on energy and water. This is a graph from a recent report from the California Energy Commission, and the projection there is that the energy on commercial buildings may level off. I'm not sure if that may be optimistic, but there are these goals of 2020 and 2030 of getting to zero energy design into the codes, right? So, which is great, and there's a lot of people already designing them today. So there's no reason why we can't get there. On the water side, I don't know, a little bit more bleak. I don't know if you can see these images very well. They're all over the internet, but pretty grim. Big drought going on in California, and if you believe what NASA is reporting out, we're possibly looking at a long drought. I was just listening to a radio show this morning where people were talking about the possibility of this mega drought and how can we learn from Australia, who they had a 17-year-long drought from 95 until 2012 or so, and so they went through this whole thing, so can probably learn a lot from them. So why is water important aside from being an important resource? About 20% of the energy used in California, according to a 2005 report from the California Energy Commission, so 20% of the energy used in the whole state of California is for cleaning and transporting water. So if a lot of times we report energy use in buildings, but if you look, you should add another 20% to that for all the water that you're using in your building, really, if you want to look at your source energy, right, which typically is not done. So it's very important. And how does geothermal fit into this? There's typically for buildings and campuses evaporative systems that are great on the energy side. Cooling towers are really good on the energy performance. And then you have air side, air-cooled chillers, rooftop units, et cetera, that are great on the water side, not so much on the energy side. And in the middle, we have this geothermal option, right? So where we can make it fit in terms of financial, it tends to be really the best fit for active systems. And we see this geothermal as a way to achieve zero energy and water in most of our projects in any case. Other things about geothermal, just HDPE as being a Type 2 recyclable plastic. There's a whole bunch of other advantages for it. Off-the-shelf components, pipe, bolts. So there's nothing here that's experimental. And then on the guidelines, this AB 2339 passed, but there hasn't been a lot of movement in terms of the standards. So Department of Water Resources is developing these geothermal heat exchange well standards. They're still in development, but currently the local water authority is the AHJ, and you have to go through that. And it really varies depending on what city and what county you're doing a project. It could be really easy and not have a lot of review, or it could be really hard. And so there's just no one standard. And why is this important? One of the things that we see that might come up, hopefully will come up in California, is if geothermal gets classified as a renewable energy, there's a lot of financial benefits. So we see that already at the federal level, and we use that a lot in our projects wherever we can to make geothermal work. But if it comes to California, then this will be a big deal, right? So we're really looking forward to that. There's that federal tax credit. There's especially the depreciation. I mean, we see there's an example here we'll look at where the payback for geothermal goes from 20 years to 2 years because of this depreciation calculation.
Marco, a question though on your costs there.
These yeah.
Costs, and I'm wondering if the vertical bore and horizontal slinking numbers, are those including equipment and complete installed system, or is that just for the field?
Yeah, so the question is whether the costs shown here include all-in costs or not. And these are costs we've seen on our projects, so you have to take this with a grain of salt, but they've been coming down, and these are the latest we've seen.
But those are for the full system.
Not full HVAC system, but full geothermal system installed. All drill rigs or whatever is needed, but not including chillers, heat pumps, all of that. So, looking at an example here to make the case of the financials on geothermal at CSU Fresno, we have a project in construction, and what I'm going to show you is not the design that was selected. This was a design that was proposed. So the client decided not to pursue a net zero energy design for this lab, but we had a roadmap. So this is Fresno. That's the site where the building is being built. Here's a zoom in into the site. There's a detention pond that the architect wanted to turn into a retention pond and have water on it the full year. There's also a well pump station right next to where the project is located. And so we had a couple of options. We first wanted to use the well pump and run basically that water through a heat exchanger. This is well water coming out of the ground that's used at Fresno for irrigation and building use, all types of uses. So you could run that water through a heat exchanger, put a heat recovery chiller on it, and get all the heating and cooling that we needed. Ended up not working because we were going to affect the water temperature by about 5 degrees, and there are certain animals that just wasn't going to work for their program, so that didn't work out. So we tried the detention retention pond, and this is the type of device that we were going to connect to the geothermal system. So a heat recovery chiller where you can get chilled and hot water. You could generate domestic hot water with this as well. So all electric system. Show you through a few slides in here in terms of how this device works if you're not familiar with it. But basically, it's a modular chiller. You could have however many modules you want. And the X's there are valves that open and close. And so basically, you could have one module in cooling, as in this case at the bottom, and everything else is being made up by the heat rejection and absorption by the geothermal. More cooling is needed, you turn on the second module. Third, if you need heating, you start turning on the heating modules, and now you're doing heat recovery across your chilled and hot water loops, and big energy benefit there. And if by chance you were to have sort of a similar load in heating and cooling, this chiller would be able to do all the heating and cooling just by rejecting the heat between the two loops. Sort of an ideal situation, but the point being that it's a pretty energy efficient device. A few more cases here. So we did some analysis and looked at several options. The option for the heat exchanger was a no-cost option because that pump and the heat exchanger was going to be installed in any case. We could get the heat rejection straight out of that, but that didn't work because of the animal research and all their programs at CSU Fresno. So the slinky on that retention pond was going to be about $850,000. And these are the energy pies, and you're seeing for the geothermal and heat recovery option, we're saving about 44% energy over the course of a year. So the last pie chart on the right. Yeah. So we gave the client this option of design and looked at, okay, we could get to about 118, 115 EUI. If you're familiar with that, EUI is energy use intensity. It's like miles per gallon for buildings. These metrics are in kBTU per square foot per year. And the last bar on the right represents the energy generation we could have with PVs on the roof. So we could almost match it. And we hadn't exhausted all the energy options in terms of energy savings like LED lighting and others. That represents lead points. The production from PVs on site would be with a 575 kW PV array. So when we look at the financials, we'll go through this a little quicker. So we're basically looking at option 3B, the one on the bottom with the red square, has the best payback in terms of compared to Title 24, 8 years. But option 2 with the geothermal and the heat recovery chiller has the lowest EUI, and it's all electric. So that would be our target for net zero energy design. But the payback was 23 years, and the client wasn't just going to take that. So we said, okay, what about if we find someone who will take advantage of the federal tax credit and depreciation? Well, what happens then? The payback comes down to 2 years, and there we go. We get the best of both worlds, right? Sort of the holy grail of zero energy design. Unfortunately, the client didn't want to take that bite and didn't go there. So we're going with design 3D. It's still going to be an energy efficient lab, but not quite as efficient as we would like it. In terms of the PV, just a couple of asides here, and this applies to geothermal in a way. When we're talking to clients about PV, and this slide is about 3 years old, the data in this, but it applies pretty much the same, except the two curves there that represent the energy costs at 3% and 5% escalation rates today come up in the graph because the cost of PVs is lower. So basically what this is showing is that if you install a PV array today, you're buying your energy into the future for the next 30 years, and you're going to get it at an average rate of about 15 cents a kilowatt hour. If you don't buy it, what you're going to pay for your energy as an average rate for the next 30 years, you can see it up there. These curves just represent the actual values, but the average ends up being 19 and 24 cents at 3 and 5%. So if you can install it, there's a lot of advantages. It pays back, and PVs have a 25-year warranty period, so why wouldn't you do it if you can find the capital to invest in it? And you're sort of securing your energy, right? So geothermal works a little bit like this. If you can invest in it for the next probably 50 years or more, you have a system that sort of secures your energy use.
Marco, the upper curve, does that take into consideration changing of tier values on, say, the gas and electric rates that are coming in 2017?
It does not, no. And yeah, like I said, this is 3 years old. Also, the cost of PVs today is lower than, I mean, it's been coming down quite a bit. So, yeah.
So should you found that they were likely to invest in geothermal?
Well, how can I put this? The client, so the university had just done a project next to this one, pretty close to this one, within this campus, where they did a PPA for the PV array. And for whatever reason, I don't know the details, they didn't have a great experience, and they just didn't have the stomach to go through another one. Yeah.
So they weren't thinking PPA for solar.
Right, that's the way they would have done it if they were going to install a PV array. They didn't have the capital cost to install it. So if we had gone this way, they would have done a PPA for the PV array and a PPA in a way, or a PPA, thermal purchase agreement for the geothermal. Can you repeat the question?
There was no concern about geothermal. It was the PPA.
Correct. Yeah, it was the PPA. So the question was there a concern with the geothermal system? And there wasn't. It was the PPA related to the PV system. Yeah. So when we add the PV array to this whole financial analysis, where the payback goes up to 10 years, but you're getting a geothermal and a PV array, you're securing your energy for the next 30 years. The geothermal system will probably be there for longer than the building will, and looks pretty good, I think. So when we look back at this graph again, we can make the cost of geothermal come down precipitously if we use these financial vehicles and have owners take advantage of it. All right, now we're going to get into the case study phase of this presentation. We're going to talk about Bullitt Center, Port of Portland. And Bullitt Center is a zero energy, zero water building. There's 2 years of data, so everything's working great with it. There's a lot of lessons learned that we'll talk about. There always are. Port of Portland these are all geothermal systems. The Port of Portland is a zero water ready project. And we'll show you what that means. Ohlone College is a zero energy ready, could be zero energy project. And this White Stripes is a campus, about 1.2 million square feet campus that is going for zero energy and water at this point. So Bullitt Center, located in Seattle, 6 stories, 50,000 square feet, about 10,000 square feet per floor. 16 UI. So again, if you're familiar with these metrics, the typical office building is maybe an UI of 60, 70, in San Francisco 60, elsewhere in the Bay Area probably 70 to 80. So 16 is pretty aggressive. 100% rainwater saved. There's a gray water system in the building. There is no black water system. We'll show you how we dealt with that. PV array, geothermal, radiant, heating and cooling. There's a natural ventilation strategy, so it's a mixed mode building, and we'll look a little bit more about those details. So it achieved, now it's certified as a living building, so it achieved all the petals, if you're familiar with this rating system, which is a big deal for us in any case. This project is also considered the most sustainable building in the world in 2013 by World Architectural Record. So, yeah, big deal for us. Here's some general info. Largest commercial building in the world. Net positive energy. We'll talk a little bit more about that. We got some slack for that, actually, from the owner. An UI under 10. So the 16 was predicted, modeled. The real UI is 10 with 90% occupancy. Zero water, and 85 is actually 90% occupied at this point. There's some images of what it looks like. Aside from the MEP systems, you can see that the building is a concrete structure for the first couple of levels, and everything else above that is timber, engineered timber. So there's a lot of timber in the Pacific Northwest, made a lot of sense, but also what you see as the ceiling is actually 2x6 on end, lined, and so that is the structural floor and ceiling for every level, and it's also the finished ceiling. So we're trying to eliminate materials as much as we can. It looks great. It's not white for reflecting light, but it's good enough. A lot of daylighting. Another image here, and here's the schematic or cartoon of how the building works. So it has 26 300 feet deep geothermal wells under the building. It has a couple of heat pumps. We did not use a heat recovery chiller for this, so there's actually 2 separate heat pumps, one for heating, one for cooling. And radiant heating and cooling at the slab level. There's also a dedicated outside air heat recovery system for ventilation. And when the weather outside is right, we open the windows. So there's automated windows in this building that, rather than have the users decide when it's going to open or close.
Could you tell us the target temperature that opening is?
Oh, for when they open? Yeah, so it depends on the indoor temperature, but generally, if we need cooling, I mean, you're looking at any temperature below 70. So we have a comfort temperature of about 78, 80 inside the building. So, and there are certain aspects about this building that are a little bit different from most office buildings, but you wouldn't feel too much of a difference if you were to work in it. And that was a big part of this whole design. And these windows, an interesting story about the windows is that they're German design, but to be able to meet the living building challenge, they had to be manufactured within 500 miles of the project. So the design team teamed up with a local manufacturer, bought the rights from the German company, and manufactured the windows locally in Seattle to achieve that requirement. And one big lesson learned, the reason why the EUI is 16 when we calculated it turned out to be 10 in operation, is that these windows are used for night flush, what's usually called night flush, that's usually done with fans. So in this building, we just open the windows overnight when we know we're going to need cooling the next day. Open the windows, cool the fabric of the building with no fan energy, and it's ready for the next day. So that's one lesson learned. We didn't realize it would have that much effect.
The schematic seems only to show floor heating for the lower 3 floors. I'm wondering what shows that.
I'm sorry. Only
following the red pipe coming up from a heat pump, and I don't see them extended.
Oh, yeah. So the question is about the schematic and the red pipes not going up all the way. Yeah, this is only showing schematically for that floor. So, but the pipes do run all the way up and down the building.
And how is the rated floor? You talked about this, like side.
Yes. Right. So the question was how's the radiant floor configured? It's a 3-inch concrete slab on top of the 2x6 on end. So on top of that 2x6, there's a 3-inch slab for the radiant floor, and below it there's nothing. It's the finished ceiling. All right. So here's the graph of the performance of this building compared to an average Seattle building, compared to Seattle code all electric. And basically when you're doing zero energy design, you have to know what your PV budget is, right? It's almost like you have a budget and you got to stay within it, or you're not going to be zero energy. So we knew what our budget was and we had to design to it. There's a lot of effort that went into modeling the building and getting it to get to an EUI of 16, or about 230,000 kilowatt hours. So here's some graphs about the top line is what a code building would have used, the energy a code building would have used throughout the year. Bottom line is what we modeled the building would use, the 16 EUI throughout the year. So here's the difference between in energy savings, if you will. Below that, the orange bars are the PV production, and these are actually measured values. And here's the difference as to we actually saved more energy. So the building ended up being net positive for 9 months, 8 months out of the year. And we, like I said, we got some slack from the owner saying, you made me buy a PV that's too large. So better this way than the other way. So let's move on to the water. In terms of the water, this is a pretty interesting story. We do capture all the rainwater that falls, and it's Seattle. There's a lot of rainfall there. So there's a 50,000 gallon cistern at the basement. We take that water, clean it, sterilize it with UV technology and filters, and then have it ready in a day tank to be used for all types of uses, including potable use within the building. Now, the reason why that was possible in this project is because the city of Seattle, before this building even showed up, started a pilot program that it will allow 12 projects to pursue the Living Building Challenge. And for that, they would have certain code exceptions that they would allow. See how it works in those 12 buildings, And if it works well, they implement it into the code, maybe. If it doesn't, they pull it back. So that's why in this building, we were able to take the water to a potable level, and there's another interesting story about that, in that even though the city at first agreed that we didn't have to fluorinate the water to make it potable, which is a requirement for the Living Building Challenge that it not be fluorinated. In the end, when the building was ready to be used, they said, no, you do have to chlorinate it. So what ended up happening is we add chlorine to the water, and then we have filters at every fixture that remove chlorine out of the water. So, so some lessons learned. So that water is then cleaned again a little bit as gray water and used for irrigation. And for black water, this building was too small for a living machine or something of that sort, so we actually ended up using composting toilets. So it is a 6-story building with composting toilets, foam flushing toilets, and that's not the toilet, that's the bin down at the basement. This is the gray water cleaning system, so some images here, and this is the nice thing about it is that if you go and use this building, and by the way, if you're ever in Seattle or you want to go there and see the building, it is open to the public. It's used as a learning tool, and there are many QRT codes where you can take your iPhone, read the code, and it'll tell you what certain systems are, so to help people understand the building. You would not notice a difference using these toilets. It's past lunchtime, so I can talk a little bit about toilets. Right. So the thing about these toilets is that they do flush some foam. I will not get into the details of it, but also the airflow goes into the toilets, down to the basement, to the bins that you saw before, the blue bins, and then out the building. So if you think about that, the usual design is that the air exhaust is usually overhead in a restroom, so the air is coming up, being exhausted up. In this case, it's actually going down, so I think it's even a better design, but you wouldn't notice a difference by using these toilets. Here's the bins in the basement, and that's actually a crank that needs to be cranked about 2 or 3 times a day.
Can you tell us what the average human occupancy is per day in the building?
The average human occupancy. You mean how? People? Oh, well, it's a 50,000 square foot. Actually, our offices are in one of the floors. They were on the top floor. Now we moved down. About 50 people per floor. 40 to 50 people. Yeah. Yeah, it's a typical office. If you go in there, you see people. There's a lot of architects, engineers, and other people in this building. Actually, the good thing you reminded me about this. The main propellant of this building, the Bullitt Foundation, is actually Dennis Hayes, and yesterday was Earth Day. He was the person who started Earth Day back in the 70s. So, background story to this building is that he wanted to have this building developed, but he could not find a developer. And so he took it upon himself. He's sort of a lawyer, environmentalist, became a developer, and had this building built. And with a lot of great results. We'll talk about financials in just a little bit. So the composting here is just organic pit moss, wood material, wood chips. And at about 4 months to 6 months, everything is dry. Somebody comes here, takes it, and puts it in some farm, non-organic, non-edible plant farm somewhere, and it gets reused. So here's some financials. It is a Class A building, triple net lease. Anybody who moves into this building has to sign an agreement that they have an energy budget. So if you're moving in, right from the get-go, you have a budget that you cannot go over. If you go over, you can trade with your tenants if they have some left over. If you can't trade, you get penalized. You pay an energy bill, because otherwise nobody pays an energy bill in this building. Operating costs, yeah, $10 a square foot. And Bullitt Center, yeah, $8. So pretty comparable. Not any more expensive to be in a living building. And then in terms of construction costs, $350 a square foot, just construction, not the total cost, which is pretty impressive. Now, this was done a few years ago. It is Seattle. Even if you add 30% and to look compared to San Francisco, you're looking at about $400 a square foot. But you know, it was a different economy back then, so not quite a fair comparison. Moving on to Port of Portland. So we're going to look at this building. It's a geothermal design as well. LEED Platinum, 51% energy saved, 80% water saved. There's a black water machine, a living machine in this project. And it has radiant ceilings for heating and cooling. Some photos of what the space looks like. You can see the panels at the perimeter there for heating and cooling. And here's a schematic of the project. So about 500 bores, 400 feet deep, 450 feet deep under the building. It's an office building and a parking garage for the Port of Portland. It has a living machine for water recycling. So black water is recycled in this project, not for potable use, but for rainwater reuse. And yeah, here's a schematic of the geothermal well. So the baseline for a building like this, the ASHRAE baseline would have been an EY of 72. This project achieved an EY of 42. This is the lobby, and this is the living machine in the lobby. So one of the interesting things about these machines is that you have to have enough stuff to feed the microbes. And that was the reason why it didn't work for Bullitt. There just isn't enough people, enough stuff to keep the bugs alive. But this is a larger project, and it worked well. And I've been there, and it's great because you have all of this greenery, live plants, and they're cleaning black water right in the lobby. There's a schematic. Capacity of that living machine is about 50,000 gallons per day. Sorry, 5,000 gallons per day. And here's some recorded data of the actual water recycled in that machine, and it shows you the cycles of the living machine. So basically, when you look at the data, the actual data, the baseline for a building like this would have used 895,000 gallons without a cooling tower. Okay, if we had done some type of design that doesn't require evaporative cooling. And this design uses 183,000 gallons, so you could easily bring that into net zero water with a cistern in this building. It didn't happen, but it could. If we had used the cooling tower, 2 million gallons. So that's the reason why geothermal systems are great. So compared to that baseline, 92% savings. So moving on to the next case study. This is the third one. There's two more, this one and another one, and we'll be done, so bear with me here. Hopefully you're having some fun. I am an engineer, so not thoroughly entertaining, but hopefully you're having fun with some of this stuff. So Ohlone College is a campus, but it's a single building campus. So it's a lab building for labs for dental and other some environmental studies. The EY on this building is 32 when you add the PV energy made up by the PV. That EY comes down to 16. So if we double the PV array, it could be a net zero building. And again, we'll look at this in a little bit more detail, but 800,000 gallons saved per year by not having a cooling tower. So, big deal. Pretty close to the bay, that's Ohlone College right there, and the geothermal is actually located in the front, towards the front of the building in the berms. There's quite a bit of slinky fields in this 5 volts in this design. There's a slinky image. Here's a diagram of how it works. So basically in the winter time when we need heating, we're removing heat out of the water, it gets cooled, and so it's shown as a blue line there. Goes through the ground, gets warmed up, and it's ready to get heat extracted from it again by the heat pumps in this building. And in the summertime, sorry, that's the end. No.
Engineers. Let's give it a second. You want to keep talking? You can. There we go.
Oh, there we go. Yeah, so I was going to show this. This is the reverse. So when we need cooling, we're warming up the water. It's shown as in red, gets cooled up by the ground, and it's ready for use again. One of the very great things about this design at Ohlone is the indoor air quality. Background story to the project is that the president of Ohlone College, Dr. Treadway, he's not with Ohlone anymore, but he wanted him and some other people wanted a naturally ventilated building. A lot of fresh air, connection with the outdoors and all of this stuff. But they're right by the bay, and so there's odors, there's also pollen, there's dust from previously agricultural land that's still there. It's fallow now, but so you get a lot of dust and pollen from it. So the compromise was that, well, we can't really do natural ventilated because of the outdoor conditions. So what goes into doing having a great indoor environmental air quality and providing a great learning environment has to do with thermal, lighting, acoustical design, ergonomics. Biophilia is something that we wouldn't have used for this project. This came up soon, but something that we're using for projects now. It's quite interesting in terms of research area. And then fresh air and lots of it. So at Ohlone, we provided 3 times the minimum amount of air required by code, so 300% of fresh air. And there's research from Bill Fisk from LBNL that shows now we didn't do this intentionally, it just happened to be 3 times, but that is the point at which the productivity peaks in office spaces. So you would think the same translates towards learning environments. People stay awake longer, feel better. And there's a lot of people transferring from the Fremont campus towards the Newark campus of Ohlone College, Newark being the newer one, this campus. Gets a lot of fresh air, filtered air, no pollen, no dust, none of that, but again, pretty fresh environment. The reason why it works in this, and it works in any project, is we did heat recovery. So there's a couple of heat recovery wheels. I think. Now I really did it.
Now you keep talking about heat recovery.
So there's a couple of 25,000 CFM heat recovery wheels in this building, and that's the reason why we were able to do 3 times the amount of outside air and virtually not really pay a lot of penalty for it. And we're doing that a lot more in our designs because of the benefits in productivity and health. That portal there is actually a portal where you can see the wheels spinning. So the building is used as a learning tool for students. There's a display towards the entrance that tells you about geothermal system, PV array, enthalpy wheel, and other aspects of the project. There's a PV array, and show me the money. Here's Newark, Ohlone College, UI of 32 and operating cost of 48 cents per square foot per year. And their sister campus located in Fremont, $3.50. It is an older campus, so it's an existing campus. It's not, we're just trying to have a baseline, not really make a comparison. But it works. So the last thing about Ohlone is there is a cooling tower. This was one of the first projects we did as a geothermal project, and it has a cooling tower and a boiler, but they've never operated. It's a little bit like Bullitt in that we had the owner buy a larger PV array, but again, we want it to be safe rather than sorry, and a baseline for the building, including all water, would have been 2 million gallons with the cooling tower included. And the design is about 800,000 gallons of water that it uses per year. And part of that, a big part of that, is the cooling tower, 800,000 gallons saved as well. All right, on the home stretch here, White Stripes is actually, I can say it now, it's LinkedIn. There's a lot of clients these days that want to be confidential, and that's the reason for that name. We didn't come up with that. Somebody else did for the client. So LinkedIn. I'm sorry?
It is a rock group, yes.
I was not aware of that. But yeah, if you've heard on the radio, LinkedIn and a few other tech giants are all vying for what's called the Mountain View, a lot of Mountain View real estate north of Highway 101, and there's a precise plan for that area because it's environmentally sensitive, although there's a lot of tech giants there like Google, LinkedIn, and quite a few others, Synopsys, many others. So the city came up with a precise plan for this whole area where they now came up with regulations that say if you want to design here, develop here, you have to follow this precise plan. And the minimum FAR has moved from 1 towards, they allow going all the way up to 2.35, and this is very important for geothermal, and I'll explain why in just a moment. And I wish we'll see a lot more of these because they want to increase the density of development, right? And this client, White Stripes or LinkedIn, it was looking to get an FAR of 1.6. So they didn't really want to go to the max. They wanted to be at 1.6 to achieve their goals. And to achieve that, they had to either, there's many options, but they had to meet LEED Platinum at a minimum in terms of energy design or sustainability design. And if they went to zero energy, they would get more FAR points, so they could go way beyond 1. If they do net zero water, more FAR points. So there's different ways to get that FAR bar up. So for this campus and the design that we're doing for this client, it's about 1.2 million square feet of land, and so they want, there's 8 office towers, about 230,000 8-story towers. And then there's also an athletic club and a theater in the same district. And this whole site has 2 levels of an underground garage. Now, that's why this makes a big difference for geothermal, is they're already doing the excavation. We don't have to pay anything for a slinky geothermal field. We get it for free. So I hope we see a lot more of these.
The underground garage is underneath the ground and the buildings, or just the buildings?
Underground, underneath. So the question is, where's the parking garage? It's everywhere. It's nearly everywhere. This is the only area that it does not have underground garage. But yeah, 2 levels. So yeah, big deal. And what we're showing here with the blue line is what would be a condenser water loop, geothermal loop, that takes water to all the buildings and then connects to its slinky under the garage. Yeah. So, and here's a calculation that we did to see what would be the load on the buildings, and if we do heat recovery like we can with geothermal, you're looking at that orange line being the load that you really need to meet. So we could get 1,500 tons out of a slinky filling out that whole site. So, which really is great news, but, and it allows us to basically take care of the cooling peak for 80% of all the hours in the year. So if we really want to achieve that peak there, it becomes really expensive to go geothermal, because then we have to do bores, and you can see the difference in cost. There's another 10 million just to do vertical bores. So, yeah, there's a question.
How far below the garage floor?
Yeah, so the elevation below the garage slab, the second level, is about 30 feet. Yeah, and the water level on this site is about 8 feet below the ground.
Sorry, I'm confused. You're saying that the slinkies are 30 feet below the lowest garage floor level?
30 feet, 30 feet below grade.
So how, but I still don't understand how far below the garage floor is, the lowest level garage floor.
So level -2, if you will. So the second level of underground garage is about 30 feet below grade.
Okay, but the slinkies are right under the floor of that?
Under that slab, yeah.
So I'm curious whether there's any issues with it overcooling the slab in the winter and over the summer.
Sure. So, well, some interesting things about this site and the design is that the water level is about 8 feet below grade, so it means that the slinky is immersed in water year-round, which is great. But
How do you keep that garage dry?
Did you laterally?
I do not know. Yeah, so that's a civil issue. I know that it's being kept dry, but I'm not sure what the design is for that. There's no sump pump planned for the site, because the slab is a tub, so it is being treated for water protection all the way around, but there's no plan for a sump or anything of that sort.
So I know one of the things with LEED is trying to keep all of the water on site, and if it can't go into the ground because there's a parking structure down there, where is that water going to go?
Right. So the plan here is to capture all the water and reuse it on site, and it's not nearly enough to satisfy all the requirements. So in a way, it works out, because we could, any water that falls on the site, we can capture it and reuse it within the building. Yeah.
This project in area?
No, this is in Mountain View. So here, just right here, close to NASA.
And is it a living building or ZNE?
So it's pursuing ZNE zero net water, but not living building. Yeah. So, so to get that extra 50% of capacity, which we're only going to use for maybe 10% of the hours of the year, we looked at several options. One of them was cooling towers. We really wanted to avoid that. So at this point, we're going to have phase change materials so we're looking at these large tanks that have phase change materials that thaw and freeze at about 60, 65, 70 degrees. We could actually pick the temperature that we wanted to freeze and thaw. And basically, we're going to freeze that material overnight with a geothermal, and then during the day, use it. Yep.
Can you tell us the life cycle of that phase change material? How long does it last before you might need to replace it?
And the degradation, right? We're looking into that. We haven't used it for mechanical purposes. We've used the phase change in walls and ceilings, et cetera, on the envelope, but not for mechanical systems. But we do know this has been used quite a bit, some in the U.S., mostly in Europe. But there's a lot of, I mean, one of the great things about this is there's a lot of 3M, BASF, big chemical companies going after this. So there's big bucks in this stuff, and there's a promising future for phase change, which really is a passive way of cooling and heating. So, yeah. So here's some energy analysis that we did and all the energy conservation measures we looked at for reducing the load, we're at about an EUI of 19 for the campus. And here's a section, again, a cartoon of what that looks like. So now you can see the garage there, 2 levels of an underground garage, geothermal slinky underneath. And there are basically French drains all the way around the site to allow the water to go in from and pass through the site. That was a requirement for environmental purposes. We are looking at radiant heating and cooling and dedicated outside air units for this project as well, similar to Bullitt. And about 49% energy savings from the lead baseline. 80% when compared to our clients' current energy use. So their EUI is about 99 right now. They have labs and office space, so there's some plug loads they need to deal with, but we're looking at bringing that down to about 19.4. So looking at the PV budget, what can we afford? The lead baseline would require all of the roofs to have PVs plus a lot of sites. The design that we're proposing today needs for PVs to be in all the roofs plus a little bit of the site. But the great thing is, in the future, we're looking at, so if you look at current PV technology, this is from NREL, there are PV cells that have 46% efficiency. They're just not commercially available, but they exist. So technology is coming, so you can see that maybe in 10, 15 years, the client would be able to be net positive, basically. So looking at water, we're almost done. Get out of the stage. I'm almost done, I promise. So water use, this is a table. I usually don't put these on slides, but just so you can see what, we looked at gray water and black water strategies, and we're looking at the savings. So we're at about 46% with all the strategies that we're looking at in terms of water savings, and that's 43 million gallons for that campus of quite a bit of water. Here's a graph of what that looks like, the campus baseline proposed, and how we're going to make that up. So rainfall, reuse of gray water, black water, and then there's also a purple pipe system that exists in Mountain View. So should we come short of that, we can plug into that purple pipe and get some water out of that. And here's the cooling tower for this campus would have used 7 million gallons. So going with geothermal phase change, you're saving that much water. And yeah, I'll end with that. So geothermal is a great way to achieve zero energy, zero water designs.
Appreciate it. With that, we're going to take a cookie chocolate water break. We have plenty of goodies over here. Get a little bit of sugar rush to ride us out till the end of the presentation. So it is about 5 after. We're going to take 10 minutes. So we're going to go to 3:15, and then we're going to fire this thing back up. Thank you.